Just a quick little thing you can check. I was arguing that you can expand the energy so this is times the mode amplitude squared as a complex quantity, of course. The point is that characteristic of a lot of these instability problems at a finite wavelength, you get something like this. This happens frequently. You may have seen it before. And all you really do is you find the minimum of this, and then ask the question, which is here, and then ask the question where that minimum first touches 0. And that's where I first get a 0 resistance to a deflection at now a finite wave vector, not the longest wavelength, which is that accommodates the boundary conditions, that is the Euler buckling threshold. And by the way, accommodating the boundary conditions is an important part of that. The Euler threshold goes up if you pin angle and position at the ends relative to free hinges. So boundary conditions appear. But so this gives a characteristic wavelength, interestingly, that varies as the 1/4 power of the ratio of the two parameters that appear here as primary importance, bending resistance and that elastic medium that suppresses the lateral fluctuations. And this is a Landau-Lifshitz problem, by the way. And what was really cool years ago was to collaborate with Cliff Brangwyn. Had lots of fun collaborating with Dave Waits and Cliff Brangwyn when Cliff was a grad student of Dave's. I think we have 6 papers together from that period. It was really fun and productive. And Cliff used to come hang out in my group in Amsterdam for like a month at a time. And we'd brainstorm. It was lots of fun. And this was one of the results of that brainstorming. On the left, Cliff, so this is a paper in Journal of Cell Biology. Amusingly, the editor, once the paper was finally accepted, we got this interesting letter from the editor back basically saying, this is the first time we've had a paper in the Journal of Cell Biology cite Landau-Lifshitz. So we considered that a success, right? It is, after all, the Bible, right, in physics. So, OK, anyway. But aside from that, Cliff was, I don't know if you know Cliff, but he's great. Gone on to much bigger and better stuff. Basically, sort of co-invented a whole new field, if you're familiar with membraneless organelles and cells and so on. Anyway, so he's now at Princeton. Another physicist converted to chemical engineering, interestingly. But on the left, he decided to just do a mock-up of this at the macroscopic scale. He put a little plastic fiber in a gel and just basically showed on the left it's in a viscous liquid. Notice the boundary conditions. It is pinned angle and position on the upper boundary condition, not at the bottom. So the shape is asymmetric, but it's the longest wavelength that accommodates that deflection. On the left is just in a viscous solvent, so let it do its thing as long as it wants, and it'll buckle at the longest wavelength. And on the right is in a gel of a appropriately chosen modulus so as to get this effect. And what was really cool is people have been interested in microtubule bending in cells for all sorts of reasons. The shapes are far more contorted than you'd expect based on the thermal persistence length. That's one of the puzzles that's been out there. But what was cool here was the initial thinking was that the lateral bends of the microtubule were all coming from active stresses pulling in different directions. Because it's sitting, you're just seeing the fluorescently labeled microtubules. They're sitting in a dense gel of other stuff, particularly near the periphery of the cell, those actin networks I talked about in the first lecture. But what was really cool is Cliff could actually, I could show a movie if I could find it. I might have it somewhere deep in my computer, but this was not a topic I intended to really get into except because of that problem yesterday. But just to tell you what happens, he could actually image the microtubule growing to the periphery of the cell, and as soon as it hits the cell, it starts to presumably get a compressive load. They actually, as they polymerize, they can generate forces. It's a non-equilibrium process. And as soon as that it touched and started loading the system, you'd get buckling deep into the cell. And so it's really hard to see how that happens without a mechanism like this Euler mechanism. So anyway. So the scale, I don't know, so a cell is tens of microns. So you're looking at something which is probably about 10 microns across. The size of the microtubules is just optical resolution limit, though. They're nanometers, and they're fluorescently labeled. Okay. The main thing for today is to continue to be inspired by this classic work of Maxwell, but start asking a slightly different question. And this will connect back up with one of the very first puzzles I mentioned in the first lecture. So okay, so at this isostatic coordination number, or connectivity, I'll just call it, ignoring all sorts of subtleties about states of self-stress possible and ordered versus disordered structures, et cetera. Basically, you know, I would expect to find a rigid system over here and a floppy system here. But one of the things we've really been interested in over the years is what happens to this picture when you add other effects. I mentioned bending last time. There's all sorts of other effects one can look at, and one which particularly gets interesting when thinking about the nonlinear mechanics of the systems that I've been talking about is to imagine a strain axis here. So think about shear strain. You could do bulk, you could do extension, you could do compression. Compression's a little different, but shear. So just simple shear. Like that. Where, you know, basically this is the tangent of that angle, essentially. Okay, I've argued that while that isostatic threshold looks potentially interesting in 2D, so this is 4 in 2D, 6 in 3D, it appears naively at least to be irrelevant in 3D because the local structure is typically between 3- and 4-fold coordinated, okay? So inevitably, we're sitting down here somewhere. So this is the relevant range where it would be floppy. But if I strain the system, I want to ask the question, what happens if I move vertically along a line like that? And by the way, I should say, unlike jammed particle systems, as you deform it, to a very good approximation, no new contacts are forming, and we're not allowing any to break. So the topology is frozen in at the time of preparation. The volume fractions are typically very low, so new collisions are pretty rare until you go to high strains. Okay, now we know you can stabilize the system with bending, but again, I want to ask, turning it around a little bit, I'm going to pull strain out of the axis here, out of the plane here, and ask what happens to the modulus. Now, technically, I shouldn't be talking about the ratio of stress to strain. As soon as I go to finite strain, it's better to think about a local rigidity or stiffness, which is the derivative of stress with strain. We'll do that. But the question is, can I stabilize the system just by straining it? Now, I wouldn't ask the question if it weren't interesting somehow, I presume, at least I don't think I would. So the answer is yes. You know this in various ways. One thing is an engineering idea known as tensegrity. If you take, so I hope you can make this out. This is a bridge in Brisbane. And you know, it looks pretty disordered, kind of randomly thrown together. But basically, if you just connect up the cables there and look at the number of them, it shouldn't satisfy this Maxwell criterion. Of course, they're cables, so they're not a Hookean response. That actually came up a little bit in Xiaomeng's lecture. So maybe you should think about something like a fishnet, right? You can stabilize it by applying stresses. So that would be where the stability comes from the forces that Xiaomeng was talking about. here, what's happening is you're combining compressive and tensile elements, and so you can get rigid, apparently low connectivity structures if you do that. But the key there is stress. Now, of course, there's other examples of this. So again, the idea is I just want to move vertically on that axis from a floppy state. Not a fishnet, but the product of spiders, right? Which are, at least some of us like them. So this structure here, obviously, if I don't apply stress at the boundary, or I want to think of it in terms of strain, if I don't pull the system out in some form, now, you could ask, is this a 2D system? Is it a 3D system? I think about its stability in 3D. If I weren't pulling on it, it wouldn't be stable, right? Now, fabric is the same thing, right? Same basic idea. You don't build things out of fabric until you put it under tension. By the way, notice tension, not just stress generally. So there's a little asymmetry there. Anyway, it certainly begins to suggest that I might cross that rigid boundary with strain. So, and this idea has been around a while, by the way. This is not entirely original. I think I'll include a reference shortly to, oh yeah, there it is. Shlomo Alexander has sadly another scientist who's no longer with us, but great polymer theorist who, among other things, talked about the possibility of stabilizing systems with stress. So that would be stress stabilized. I want to think about strain. Now, let me just show a movie. It's not a movie, it's a cartoon. Let me show a cartoon to just illustrate this point. It's interesting. It's not exactly what's showing on my screen. OK, so I'll do this again, but so I should have warned you. Start with a triangular network and dilute it randomly. And just ask the question. Now, this happens to be bulk strain. Just strain it at the boundaries and ask the question, is it stable? And I assure you, throughout the region of deformation there, if you were to measure a shear modulus on top of that strain state, it would be absolutely zero. Entirely floppy throughout that region. It's just about to undergo a transition and become rigid. But let me back the movie up and show it to you one more time. Well, no, let's actually see it go rigid. So I'll play the whole movie again. But I should also say that as the system is being extended, the image is being reduced in magnification. So the whole sample is still in the same field of view. So equivalently, you could say all that I'm doing is I'm taking the connectors and I'm shrinking them. This was actually a paper about active stresses, contractile stresses, so that was really more what's happening in that case. But there were rearrangements you saw. I'll say more about those rearrangements in a moment. But let me just continue. And as you strain it further, I doubt you can make out, but if you look, well, maybe now you can see that there's some red lines and blue lines. The blue lines have no tension. The red lines have tension. And obviously, so this is not a spider web now. It's a drunken spider web, but the idea is the same. You're pulling it really hard at the boundaries. You've stretched things out. You've pulled out the floppy modes, you could say, and what you're left with is stable. Tension can actually propagate from one side of the sample to the other. Yes?
That's an isotropic strain that you're applying?
This happens to be isotropic bulk strain. Yeah,
okay.
Exactly, just extension. By the way, notice this doesn't work under compression. So this is one reason. So there's two reasons why I want to focus on shear ultimately, but this is just to motivate it. This is experimentally the most relevant because all the networks I've been talking about are actually sitting in a solvent. Solvents are incompressible. So if you want to study the network properties, you want to study a volume-preserving mode like simple shear.
I mean, that's sort of true because the fluid can't drain from the
Yeah. So you get into some interesting hydrodynamic effects, two fluid effects. You've got two components. I'll maybe say something about it later, but you're absolutely right. I'm assuming that on at least on short enough timescales, the network inherits the incompressibility of the solvent it's in.
Yeah, I mean,
short enough timescales.
I totally agree with everything you're saying. And then here, you're also not including bending, right?
No, this is just Hookean. This is literally Maxwell strained. Maxwell was linear stability argument, right? So you could say this is just the Maxwell idea applies finite strain. Now let me play the movie again because I want you to notice those rearrangements. One more. Some subtle rear. Now, why is it not playing?
It was playing. What is the difference between the blue and the and black lines in the figure? Is it the sign of the strain?
Hang on just a moment. So, there we go. Notice it's no longer really triangular, it's starting to rearrange. Can you imagine those rearrangements are getting large right before the transition? Think critical. And your question is the different color lines?
Yes.
So that's, at this point, they should all be blue lines because nothing's under tension. So that's probably just an imaging, artifact. If I go further, and there's still some large rearrangements that happen, and then they die down as you strain the system hard. At this point, red lines start appearing. Those are under tension. Yes?
So the lines also start overlapping. Is it allowed?
Oh, yeah. So we treat these as phantom. They're allowed to overlap. Again, the volume fractions are low enough in a real system that those are rare events. I should point out, the transition was actually occurring at 10% strain. So that's not a massive strain. Those rearrangements were not really massive. But when you get up to strains of order 1 or higher, then you've just utterly collapsed certain regions, and you've probably started making chains overlap. So that's unphysical in that extreme strain regime. OK, those rearrangements play the role of critical fluctuations. One of the things, so while the idea of strain stability, stress stability, or whatever, is something that has cropped up in the classical polymer literature, among other places, over time, it wasn't really known what the nature of this transition was. So this was a puzzle, and it was a little hard to sort out. It technically, well, actually, the 2012 paper, if you read it, we remained a little agnostic at that point because it was difficult to identify, because there's mixed features of first and second order like transitions. There's discontinuities, but they're not in things like the order parameter. Anyway, over time, we've come to realize this is a line of critical points. Second order like critical points. So this is a critical point no doubt with different critical behavior, but this line emanating from it actually remains critical. And that's basically what I want to convince you of first. OK, but the idea at least clear? Strain can stabilize, but what's the nature of the transition? That's basically the question. OK, so if that happens, then here's the kind of thing you might expect. Strain is now going to be my control variable, moving along that line. There's a floppy phase, transitioning ultimately under appropriate conditions to rigid. There'll be a critical value of strain separating those two. And for instance, if I were to measure something like the modulus, I'm going to argue you should look at the tangent modulus. Then you might imagine something like that if it's critical. Here's one of the subtleties. Turns out that there is a small discontinuity here, but it's not a first order transition. The reason it is, I'm going to ultimately argue this is not an order parameter. In spite of the Maxwell argument, where the modulus is an order parameter, this is much more like a heat capacity. Heat capacity winds up being, you can certainly have discontinuities in the heat capacity. Even the mean field treatment of the Ising model has that. OK, so anyway, this is what would happen in the absence of any other effects that stabilize. Yep.
Does that say that stress should have been there?
Well, so you could look at either stress or this. Yeah, either one would be it's not an order parameter. No, it's still not an order parameter. Stress is analogous to entropy. I'm getting slightly ahead. I hope I'll convince you of that. But I just want to warn you, one of the reasons we had some difficulty identifying the nature of this transition has to do with discontinuities that it can appear in the original Maxwell picture of central force only. But the more relevant case to experiments like collagen is with bending. And so if I add bending back in, I'll get something like that. Okay? So this is now with bending. And so that's the kind of signature we should see. Different levels of bending rigidity will stabilize the system to different linear moduli here. So the intercept here will be a linear modulus. But in general, the curve is the derivative of the stress-strain relationship. Okay. Moreover, you could expect, for instance, K would look something like this. If you imagine that behavior right there, ignoring for a moment possible discontinuities, then, you know, in the high strain regime, I've engaged, if you like, all the filaments. There's lots of tension. I get a modulus which will go like the line density of filaments times the modulus of those to further stretch. And then this factor here takes into account the fact that I get a vanishing. This exponent is not the exponent we looked at before. It's not far from it, but it's a different exponent because I'm measuring. So gamma, if you like, is like temperature in a normal thermodynamic phase transition. Now, that's all true in the region above the transition, the ordered phase, you could say. What happens below? Well, let me just show you some results. So on the lower panel are those curves from various computational models. This happens to be a 2D system with bending rigidity and stretch modulus. The curves are, well, you know, on a log-log plot, they're basically like this. Notice the orders of magnitude increase that occurs near the critical point. So the dashed vertical line represents the boundary where the modulus would have vanished in the absence of bending rigidity. For technical reasons, that happens to be the hardest case to look at, oddly enough. Finite bending is easier. So that's one reason why it's not shown in this curve, this plot. And then the upper red boundary happens to be the affine model. It's not a flat line, and that just has to do with the fact that as you strain a system hard, it's no longer isotropic. So the isotropic argument that gives the prefactor here has to change. That's not interesting, I would say. It's a small effect. It's just like a factor of 2 at most. Right. Now, what's shown above are experiments. That's collagen. I think I've shown that kind of experiment before. It's a little compressed. Notice the 2 orders of magnitude stiffening. More than, it's like 2.5 orders of magnitude. That's one of these reconstituted collagen type 1 systems. Certainly looks qualitatively similar to these computational curves. And what I want to do is say, well, what happens with bending? So I'm just going to take a page out of the critical phenomena sort of scaling analysis and scaling functions that we've seen before. So basically what I want to say is what stabilizes the network. So what I wrote down before should be correct without this function. Just let that be 1. That should be on the right-hand side. How do I capture what's on the left-hand side? Well, I have to have presumably some scaling function. This is really an ansatz that you assume. And I would expect a combination like that. Yes?
So I have a question. So have you considered if there is any way to map this problem with jamming? Because jamming is like you have one-sided repulsive potentials, compressed stress. They will run, and then state of cell stress appears.
The one that looks more like that is not this, it's a rope limit, I would call it. So it's a system that has no resistance to, actually you talked a little bit about that, right? The question about the fishnet, I think, in your lecture. If you really take a system that has no resistance to compression and only resistance under tension, that I would call, in the literature, at least in the fiber business, it's often called a rope limit. That rope limit would be the one that might be analogous to jamming, not this.
So here you actually need a compressive.
No, I don't need any stress. This is perfectly stable at, well, hang on. This stability here is stable at 0 strain. It's the bending which is stabilizing it, and it's harmonic. It's locally harmonic.
Yeah, I mean without the bending, if you don't have bending.
Yeah, I would say it's still not quite the opposite of jamming because I still have Hookean springs that resist compression.
Right, but maybe the transition is similar if you turn off, if you just have cables.
Yeah, so the cable one or the rope one would be the one that would be most analogous. The strange thing is that's still non-mean field. And so if you map it onto jamming, it's not going to work, right? So there does seem to be an interesting subtle difference between the two. But yeah, I agree with you. There's something at least qualitatively similar about a rope limit and jamming maybe. They're sort of opposite in terms of the deformation you need. Okay, so what should this scaling function do? Well, a couple things I want to point out here. I'm introducing a symbol kappa tilde. It's a dimensionless measure of bending rigidity. So I'm really interested in the ratio of bend to stretch. These have different units, so I'm off by 2 factors of length. This is energy times length, this is energy per length. So I divide out by 2 factors of the natural network length scale, distance between constraints, mesh size, you could say. This is a dimensionless combination of this. And if you plug in what this is, we've seen this before, but let me just remind you, if that's a Young's modulus, well, it should be proportional to Young's modulus times 4th power of the diameter of the fibers divided by Young's modulus 2 powers for the stretch modulus, and then 2 powers of this length here. That is just volume fraction, because it's cross-section area. So take a network, slice through fibers. If I take the area of the fibers divided by the area per fiber, I get the volume fraction, because this is the spacing between fibers, essentially. So this is proportional to volume fraction. Excuse the multiple use of symbols. I'm going to use this. An exponent phi here, but it shouldn't cause any confusion. The context is different. And so then what I would expect for this function is the following. It should have 2 limits. So if I'm above the transition, this should go to a constant. And if I'm below the transition, it should go to some power. But what power does it have to be? Well, if this is proportional to the bending rigidity, and I'm supposed to recover a bending-dominated elastic regime, except for the case where that molecular weight is so high that I talked about last time, where I actually recover an affine limit even in the linear regime. So provided I'm not at super high molecular weight, I would expect this function here should go to a linear behavior so that I recover an overall modulus proportional to the bending resistance. By the way, notice the mu cancels out then. And so what I wind up getting is an overall linear modulus, an overall modulus which is proportional to bending resistance times the square of the volume fraction. Okay? That low non-affine modulus from before. Okay, so does this work? Well, first of all, let's look at that exponent f. What is it? Well, you know, you do careful estimates of it, and it's pretty clear it's some number less than 1, about 0.7, 0.8, okay? So that's just to show you that, that exponent is less than 1. 1 happens to be the mean field expectation. And again, for the two regions, call them plus on the right, minus on the left, I expect, oh, I guess I called it W here for Whittam. There we go. And there's actually two of these functions, one above and one below the transition. And this is just to remind you, above the transition, I expect it goes to a constant. Below, it should go to a linear function. The only way for that to be consistent is if they have a common scaling with some other power at high values of the argument. And so let's see if that works. So what we do is just take the scaling ansatz, take those computational data I showed you before, and see if there's an f and a phi such that this works. And here it is. All the data collapse. There's 3 different colors. Just look at one color at a time. The lower branch of the function is this behavior. The upper branch is this behavior. The branch on the far right is actually the critical, going to the critical point because this argument is vanishing, making this large. And so, you know, it's pretty clear you can extract exponents there by, you know, if nothing else, just using different values of f and phi. So we extract those. Again, the f you can independently get based on the picture I showed before. But let me just remind you of what this would look like for ferromagnetism. For ferromagnetism, magnetization would go with a very similar sort of scaling picture, different exponents. But now notice what I'm saying. I'm saying that what plays the role of the magnetic field in that ferromagnetic transition is this kappa. Now, it's not a field that breaks the symmetry in the way, so careful with that analogy. This is a loose, I just simply prefer to think about a stabilizing effect in the sense that a field gives you a finite magnetization, even in the disordered phase. But at least mathematically, the claim is that these scalings should be very similar. The traditional exponents are beta and delta for those. Now, you can take classic, this is 100-year-old magnetization data in kind of funny units. And in the 60s, well, people replotted this. That's a really weird way to plot it. Let me rotate the figure. And if you rotate that figure, it starts to look like, well, it identifies this function W. Actually, this was just W minus. And you see the paramagnetic phase is where I get a linear relationship between magnetization and field. Sorry, field is up here.
What are the limits of the scaling function? Because the limits are the same. At least,
Sorry, you're absolutely right. This is for plus. Sorry, this is for minus, and this is for plus. There's 2 branches. Yeah, thank you. Sorry, you're right. I'm not looking at different ranges of x. I'm looking at small x. Yeah, sorry, this is a little confusing. It's small x, these 2 behaviors in these 2 regimes. Okay, so that looks, you know, pretty similar. You know, the computational world, the ideal world, is one where you have more orders of magnitude to play with typically, so if you're lucky. And so, you know, this is a wider logarithmic range than real data in the case of magnetization. But how does it compare with experiments? So just before doing that, I argued that what this should really depend on is essentially the volume fraction. I can't independently control the bending rigidity of the fibers. That's, to some extent, our colleagues can do that, but the volume fraction you can certainly vary over an order of magnitude. A little over. Strain, the beauty of this, by the way, contrast this, by the way, with the isostatic point. The isostatic point, if you want to study it around the critical point, you've got to make different samples of different connectivity. Or in the case of jamming, you can create the different connectivity by straining it. But at least for these networks, this is controlled by the chemistry of the preparation somehow. The beauty of a strain-controlled transition is experimentally, that's standard machinery. You pop it into a rheometer. And so, in principle, you can study this as with the precision that your instrument has for strain, okay? But anyway, so what I should do is take K divided by, so this is also proportional to volume fraction, right? Rho, the line density. I'll just say C, concentration. If I take K, divide by concentration, that'll take out this factor. The mu is just a property of the fibers. It presumably doesn't change, slightly subtle point, but doesn't change as you vary the concentration. Divide by this factor. And plot that versus concentration divided by this factor. So can we take experimental data and do that? Well, so actually the reference is gone now, but I had it up before. So my colleagues, so Gijsje Koendering's group was doing these really quantitative rheology experiments, and we were just shocked when we saw the agreement. On the left, this messy collagen sample, highly disordered network. Messy's I'm not complaining about them, they're actually beautiful networks, but you know what I mean, it's a highly disordered system. How in the world could it show this scaling behavior almost as cleanly as a solid state system, right? So anyway, I should say a little bit more about this. Yes?
That's an experiment, right?
That's experiment. That's collagen.
And the scaling function, it has a different slope. Or is that C to 1/2?
So what's going on is the following. When they vary the concentration, there is a slight shift that can actually be, to some extent, measured. It's tough to do by imaging alone, but they actually see that the connectivity slightly shifts. Sorry, the connectivity. So the critical point slightly shifts. They can account for that. So what they do is they take the networks, identify the critical point. It happens theoretically to be the inflection point on a log-log plot, so they can identify that. But because the connectivity is shifting with concentration, as you go to higher connectivities, you slightly increase the coefficient here as it happens. And so it is a slightly stronger than concentration dependence that you get here, okay? You can account for that. So there's another prediction of the model which has to do with the strain at which the system goes nonlinear. That should have another predictable dependence on connectivity of the network because that's basically where you are on this boundary. And so one of the things they confirmed was that the concentration dependence of that was consistent with the shift in the concentration dependence in that lower branch. But you're right. Yeah.
I'm not sure I totally got that. So if I look at different points along, I guess, Z, which would be concentration, the x-axis?
Yeah, so this is a very, so let's see. This, what they find is this varies very weakly with concentration, not proportional to concentration by any means.
Yeah.
And so that means that when you compare it, so this is samples at 6 different concentrations spanning almost a decade. So there's slightly different points along this curve. And what we're really assuming is that the critical exponents in that region are not changing.
Right, that's what I was going to ask, is whether or not the critical exponents
No.
change as
So
you get away from ZC.
We don't allow for it, and then the confirmation of that is how well it fits the data.
But your range of concentrations, I guess an order of magnitude is
About an order of magnitude, yeah.
not bad.
So remember, the linear moduli are varying by 2 orders of magnitude if you vary the concentration by 1 order of magnitude. So the actual raw data, actually I'll show the raw data curves in a moment.
Yeah, I guess what I'm trying to figure out is, do you think of it as a line of critical points or a crossover between 2 different critical points? In other words,
No, we really think of it as a line of critical points.
what would be the difference? I mean, like what I'm hearing is that the critical transition at ZC has different exponents, and everywhere along the line, it's being controlled by a different exponent.
Potentially, but in fact, we computationally confirm that the exponents don't vary over quite a wide range.
No, but that's okay for crossover transitions, right? Like if you have a crossover from a critical point, like the Heisenberg to Ising magnet, the Heisenberg critical exponents only matter at the critical point where there's no symmetry breaking in the Hamiltonian. The minute you leave that, everything is controlled by the Ising critical point. Is that not? Yeah, so anyway, I'm not sure. I'm more asking than saying. I just don't know what the difference is between a line of critical points versus a crossover transition. And
so
maybe Danilo is actually the...
In fairness, I have to say, so it turns out we do have a good mean field description for this now. It's highly technical. That's that paper I mentioned yesterday. I don't really want to get into that, but actually that paper, yeah, we haven't actually submitted or even finished writing the one with the critical, as it happens. But you can get a mean field theory for that. Now, of course, it won't get the exponents right, but that's the kind of thing that could start teaching you whether it's a genuine, everything points to the fact that it's a genuine line of critical points. Can I rule out a crossover? Well, I'm actually going to return to this later. There's all sorts of additional parameters that this can depend on. So it does get a little messy, I admit. So at this point, the evidence is the computational model on the theory side and agreement with experiment. So if you like, basically, what I'm saying is this ansatz for this scaling function seems to work. Yeah, question back there.
Just, I'm not sure if it's a dumb question, but is it like, would it be possible that this line is a first order transition line instead of a second order?
Well, it's definitely critical. We find diverging fluctuations and diverging correlation length along the line. So all those signatures also hold. It does not appear to be first order.
I'm just wondering if that could be like some kind of, when you measure the strain on the fiber networks, if you have like floppy regions coexisting with rigid regions, somehow of coexistent region between this line, or close to this line.
It's a disordered system. There's no doubt locally slightly more rigid, locally slightly more floppy regions. But no, all the other critical signatures are clearly pointing away from first order. Sorry, Xiaoming, you had a? I saw her hand up quite a bit ago. Hang on, we got several questions.
Okay, yeah, I think my question is related to Itai's question. So is it right to think that there is a fixed point and you have a line of transition, but it's controlled by that fixed point? So it's like as soon as you go to z less than zc, it is controlled by that new fixed point. And there is a line of transition, but the exponents are controlled because the system flows to that new fixed point. So it's one universal set of exponents.
Well, we certainly don't see the same exponents. That's for sure.
I mean along that line.
Yeah. So that would be consistent with what we see. we see that there is, if anything, there's a weak variation in the exponents here.
There is, you mean?
There is. It
Okay,
does appear to be real, but not on the scale that can be measured experimentally. So meaning that the experimentally accessible range here is pretty narrow. If you go way to the extremes, you will, at least numerically, see apparently different exponents.
So it can be computationally studied in
Yes.
lattice models, right? You can vary it a really large range.
Yeah.
Yeah.
So we have the most dynamic range in 2D, not surprising. Interestingly, I should have pointed out the curves I was showing you before were 2D and 3D. So we can do this in 2D and 3D. Amusingly, the difference in exponents between 2D and 3D is small. It's not large. But I have to say we haven't fully resolved this. But there is evidence of variation along this line, which is weird.
I see. Yeah, yeah.
I think, okay. Is it on? Okay. So even if the critical exponents didn't vary along the line, the critical exponents along the line are different from the ones at
Yes.
gamma equals 0, right? So in the vicinity of that point, there's still crossover scaling.
Yeah, yeah. So by the way, you can definitely do that analysis right near here. Yeah. So I should have probably pointed that out. That's actually something you guys did with Herbie at some point, right? Yeah. So yeah, so if you study the system near the isostatic point, you can do that crossover analysis here. And what's interesting is that the exponents you get even there clearly vary when you get far away. And so our take on this is that while in the larger sense there may well be this deep connection between this point and this line, there doesn't seem to be, I mean, we haven't seen anything predictive other than qualitative features, like, you know, ignoring the values of actual exponents. But there doesn't seem to be anything predictive from that analysis here deep into the subisostatic. That's what I would say so far. I think you had a question.
You mentioned about correlation.
Yeah.
Correlation. What are you correlating?
You mean the fluctuations?
Yeah.
And the correlation length? Yeah.
Correlation.
Can I get to that a little bit later? So this transition, so the cartoon I showed you with the rearrangements were getting large right near the transition. If you look really closely, they're also of larger scale. So the non-affine fluctuations become larger scale, actually diverging scale at the transition. Yeah, and that plays an important role because I'm actually going to, so I do want to get to a, I do want to get to a way to analyze this in a sort of real space renormalization picture, okay? A la Kadanoff. Yeah.
So what happens when I take a floppy network, strain it a bit, but I keep under this line, but then add more bonds? Becomes it rigid?
Yeah, so in other words,
at the same line? Or,
in other words, you want to do this.
Yes.
Yeah. So obviously, experimentally, that's the harder thing to do, but it's certainly doable. Yeah, so you, in principle, could cross this line different ways, right? You could take different trajectories across it.
But so becomes it rigid at the same line, or only at this, when the C is 6 or 4? So
I think it becomes rigid at the line, exactly at the line, right?
Yeah. Yeah, sorry. The line really separates. It's a genuine phase boundary. So it really separates rigid and floppy. And so let's see, Yeah, so again, the typical values are about 3.5 plus or minus about 0.2, so it seems to be the experimentally accessible range for something like the reconstituted collagen type 1 networks. So indeed, that's well below 6, so you're up here somewhere. It is amusing, if you go to 2D systems, of course, where this would be a lower threshold, you get a similar line, and by the time you get up to 10% strains or so, those lines appear to basically be the same. They're not the same, but the difference in strain is not big.
That has to do with the rigidity percolation.
Well, no, I would say it's separate. Well, so there's multiple transitions going on here. Down here deeper, there's a rigidity percolation transition too, with bending. Yeah. So we're in the window between those two. And the influence of those two critical points on this line, you know, those are subtle questions which I have to say we're still sorting out. Okay? Yep.
No. You can go ahead.
Okay. So, yeah, all good questions. And, you know, we're still sorting this out. So I have to admit that. Let's just take this idea, though, and now remind ourselves of the sort of a bigger phase diagram. So, sorry? This line represents the, what I claim, critical line, genuine thermodynamic phase transition, happens to be at t equals 0. Of course, everything's t equals 0 so far. I'll relax that, hopefully, if time permits. But this is 0 bending. As soon as I go to any finite bending rigidity, so if I were to bring out another axis here of not strain, which is what I think I plotted at some point, but bending rigidity, then I lose that critical line. I go away from the transition, and then definitely I get smooth behavior, no particular singularities. And so imagine looking out in that volume along that trajectory I sketched over there, and then rotate the picture, and you have something like this. You've got a critical point down here. You're going from what would be floppy to rigid, but as soon as I've got bending resistance, it's really from soft to hard. They're not qualitatively different. It's not a phase transition, but I go through a region which is a critical zone in, you know, strongly under the influence of that underlying critical point, even though I'm not going through the critical point. And what's the signature experimentally? Well, here's a blow-up of that experimental data for just one of the curves. And so the open symbols, again, are showing 2.5 orders of magnitude, actually more like about 3 here, of stiffening. The red X happens to mark the actual critical point. The blue is something my experimental colleagues like a lot, which is just sort of the empirical point at which the system goes significantly nonlinear. And the dashed curve is just taking a page right out of the ferromagnetic analysis. You basically turn around this, you make a ansatz for the scaling function that agrees with its exponents without worrying about whether it's the right one or a universal one and all those things which I think you heard more about from Jim. But just take that as sort of empirical fact and invert it to get an equation of state. Now, this is an equation of state. Again, naively, the capital K is playing the role of magnetization. Kappa is playing the role of field. So this is field in terms of magnetization. You can invert it and get a relationship as a function now of strain for different values of kappa. But let's see if this picture makes sense. So first of all, you can do this you can fit simultaneously a family of curves. So these are all the different collagen samples. Actually, there's multiple samples, but different concentrations. And notice the linear moduli are varying over a little bit over 2 orders of magnitude. These are different curves. you do have to account for the fact that the critical points are slightly shifting. Yeah.
That's quick. The calligraphic K is just the K, the capital K, the modulus, right?
Yeah,
Okay,
stiffness.
Okay,
yeah. Oh yeah, sorry, I guess I used a slightly different symbol there. But it's just that. And so one of the things you can do is you can just take this family of curves, fit it, and extract the parameters you get. Now, I should point out it doesn't quite have as many free parameters as it looks like, because the phi and the f we get from the computational model. And as I said, to within our error bars of identifying them, over the experimental range of varying connectivity, they're not changing. If you go well outside that, they do seem to vary. So those are not fit parameters. The only real fit parameters are the critical strain, and you do that empirically curve by curve, because they do shift around. They're different samples. And once you take that, the only remaining fit parameter is this bending resistance. And I argued that that should scale as concentration. And sure enough, empirically, that is scaling linearly with concentration. So the picture seems to fit. There is, at the same time, there's some interesting finite size effects indicating a diverging correlation length I'll get to in a moment. But this is just basically what's directly experimentally accessible. It's very hard experimentally to say anything. By the way, there's been a lot of work on that about the fluctuations. Yes? It's, so that red zone you should imagine as the range over which what would have been a singular jump in the modulus on a log-log plot, it just spreads out. And so notice at low concentration where you're closer to this critical point, it's steeper than above, okay? So all you're doing is you're taking out that, taking that vertical line and sort of spreading it out. Okay, so you know, the critical phenomena is, of course, something we had a lot of fun with. But you can use this as a basis for a predictive theory for collagen, including both linear and nonlinear regimes. And I just want to quickly illustrate that. This is, again, from a work of Karen Janssen when she was a student with Gijsje Koenderink. I just love these images. Aren't those beautiful? You can see the structure of the collagen, the sort of, again, this is collagen type 1. You can see each one of the fibers is really a sort of braid, et cetera. But just to sketch the kind of thing you can do, you can get a, you can extract basically from the model, you can extract, actually together with some scaling arguments I don't have time to go into, you can actually extract a prefactor for this relationship. You can compare that with experiment, and it agrees quite well over a wide range. I should say there's still one big unknown. There isn't better than a factor of 10 agreement on what the Young's modulus of the fibers is. And so the vertical scale we're just allowing to be free. All we're doing is comparing different samples assuming the same Young's modulus, okay, for the collagen. You can also get relationships between various quantities which are experimentally measurable. So one thing I like is a sort of, you can think of it as a sort of susceptibility. Remember way back to when I showed you the collagenous tissue data of Feng, that there was this approximately linear relationship between the stiffness of the network and the stress applied. One of the things that comes out of this model is a approximate linear relationship between the, and it is approximate, but it's pretty good, between the modulus at different strains, so this is nonlinear, and the stress, but it's not the shear stress, it's the normal stress. So when you apply shear stress to a sample like this, what happens for these systems like collagen, they develop significant traction forces along the axis, okay? Interestingly, opposite of what incompressible polymer gel would do. That's an amusing story in itself, so-called negative normal stresses. But these are measurable at the same time, and the prediction of the model is an approximate linear relationship between that. And that does come out pretty well. Notice this is samples under radically different preparation techniques, different concentrations, et cetera, multiple samples here. And moreover, there's a predicted relationship between that coefficient, that sort of susceptibility, and the strain at which the system goes nonlinear. That's the predictions of the models. This is the experimental data. So there's a bunch of other tests you can do. And so ultimately, you wind up with a good quantitative basis for predictive model of collagen, linear and nonlinear. Yeah. And then we should probably take a break and have some questions. Right, 5-minute break, including questions. A stretch break, I guess.
Do those things age? Because we know that it does age in the real life.
Yeah.
So if you take, let's say, tissues or collagen, different samples in animals, do you observe a different behavior? Do it change the mechanics?
So I should say that by design, these experiments are focusing on a simple elastic regime without plastic deformation or aging, which does happen. Okay, so so basically, when the data I showed actually can extend a little bit further, but you go into a plastic regime. So we intentionally removed the data beyond the point at which it was reversible. Okay, so empirically, that kind of aging was left out of the was left out of the data that was even being analyzed. Okay.
But
it's interesting. Yeah. In fact, collagen is fascinating. It is well known to undergo a particular kind of so-called working in the material science sense, where you go into a plastic deformation state, it doesn't return to its original state, but about that new state, it looks like the old one, et cetera. Okay, so let's have that short break.
So 5 minutes, you say?
Yeah, 5-minute stretch break. And I want to get back to how we understand this critical phenomena a bit more.
Yeah. So if you were at even lower Z, for instance, you would have a rigid percolation transition at zero strain. And then if you turn on the strain, do you get a transition there? I mean, do you get a rigid phase after you?
Well, so actually, the other critical point we've been more interested in is you can ask the question, where would this line end? Well, if I'm allowed to go to infinite strain, imagine that cartoon I showed. You'll get a stable system provided there's a connected pathway.
Yeah.
That's conductivity threshold, not bending rigidity threshold. So the actual lower bound, the asymptote that this approaches is actually the conductivity percolation threshold.
And how does that compare with the other?
The bending one is a little higher.
So you would get
you can have a conducting pathway without having a...
And the conducting pathway probably has the same Z value for 3 and 2D. Which is why they merge.
It's very close. I've actually forgotten the numbers.
But that's why they probably merge.
Yeah.
So you can have bending and be floppy at the beginning, for instance, if your Z is smaller than rigid percolation, and then you turn on the
yeah, actually, by the way, about rigidity percolation, remember this picture is kappa equals 0.
I know.
So, yeah. But the relevant lower limit to this curve is that conductivity threshold.
I get it.
But it only asymptotically reaches. And indeed, in 2D, you get you get curves that look sort of like that. Yeah. They're not far apart. I think physically that makes sense. By the time you strain the system significantly, it doesn't know what its original structure was so much, including the dimension it was embedded in. That's a rather, simplistic way to look at it, but that's my intuitive one.
So is that just for polymers? Regular
Fibers.
But I mean, kappa is equal to 0. It's bending rigidity is 0.
Oh yeah, but T is equal 0. Still not polymer. Still not flexible polymer.
So when you shear to prepare the system go across the transition, is it also rigid with respect to other strain, or only for that shear?
Yeah. So all the experiments are at finite kappa. So they all have all the moduli are non-zero. Yeah. You can't ever. So sadly, maybe you can't ever really directly access that line. All you can see is its influence away from the critical line.
If you shear it like this and then measure the transverse modulus.
That's almost what this is doing. So this is shearing and looking at stresses, but you could also do the other thing. Actually, Paul Janmi at some point was doing a series of experiments like that. I don't know if you guys do it, but you shear one way and ask the question about stability in a transverse direction. That's kind of what this normal thing is doing.
That's what we do.
Yeah, exactly. Yeah, because that's what
Yes.
that's what loading is.
Well, no. So I mean, we do this in the context of shear thickening suspension.
Oh yeah. Mm-hmm.
So in those situations, the orthogonal shear breaks up the force chains.
Yeah.
Or the rigid clusters, and so you end up getting de-thickening. So it's basically a
Yeah, won't happen here under the assumptions that the topology is fixed. So yeah,
But what is
it is an.
What does orthogonal do here?
So I think it's fairly trivial in this case.
It's just testing how close you are to a completely stretched structure.
Yeah, I
Because
mean.
if you do orthogonal, you're
So
essentially
if the strains are modest, like
That's the point.
10%.
So if you're to know how close you are to completely stretched, you would do an orthogonal that would stretch it out even more, and you'd see if you're like in the limit.
Yeah.
Versus if you have a lot of give, then you wouldn't get much difference based on this. So it's like a susceptibility to how close you are to the completely stretched.
Yeah, the reason we focus on the normal one so much, by the way, which is an orthogonal direction, is it's just known now from a lot of work going back to stuff, we've looked at with Paul Janmi for years, that the normal stresses are anomalous in these biopolymer systems. And one of those anomalies is a so-called inverse pointing effect. If you take an elastic rod and twist it, most elastic rods slightly elongate, very slightly. These systems have a tendency to do the opposite. But it depends on coupling to the solvent. So it's the time scale you look at.
Yeah. Yeah.
So if you,
But they're kind of set up to study normal stresses quite a bit. That's why we looked at that.
I heard you say if you turned on bending rigidity,
The line goes away. I mean, it's no longer critical.
But this one that appears is connectivity percolation. Is that?
Yeah. So as long as you have as long as there's some connected pathway that goes across your system, once you've strained the hell out of it, that's going to bear a load.
So are those exponents controlled by connectivity percolation?
Yeah, I don't think so. We don't see any evidence of that. But the thing is, this asymptote goes out to super high strains.
Okay.
So, yeah, it's.
Yeah. But if you thought of it as a crossover, then
Well, yeah. I mean, it
that
sounds like,
might be.
well, so this is completely destroyed as soon as you turn on any kappa, even this kappa.
Yeah.
So.
No,
So,
and
should
it's
we
not in a-
get started? Yeah.
It's not in a first order. It's not like that's a critical point. and
No,
then
it doesn't go first order. It just goes smooth. There's no transitions. There's no thermodynamic boundary. I would say there's genuinely no thermodynamic boundary.
So in the kappa planes, it's like kappa non-zero. This is the only genuine transition.
Yeah. So if I take this out into kappa, I get this figure I showed, gamma, critical point here, and just a zone.
Right. Yeah. Okay, but then there's the genuine.
Yeah.
Think about
Okay.
language.
Okay, so in the last few minutes, I want to sketch for you how one can start to understand this behavior in a, I mean, of course, what we would love is, a full analytic theory here that we could do whatever we want with, maybe even a normalization group, you know, whatever. Instead, let me try to sketch for you a framework which starts to teach us new stuff. I happen to think, I'm very excited about that recent preprint where I think very significant progress within a mean field context, at least we have made here. It's highly technical, I don't want to go there. It doesn't in any way change the following sort of conceptual picture. So what I want to talk about is actually it's inspired by Kadanoff's real space sort of picture, or normalization picture, and how that starts to be useful in teaching us certain special scaling relationships between some of the exponents, okay? So the basic idea is the following. You take, so I'll use the language of spins on a lattice, but of course a lattice for us is one of these meshes in a network, okay? And the basic idea here is to say, okay, so I want to study that line, right? That's that line over there I've sketched. And so naturally, the control variable becomes little t. I'm going to use t because I want the intuition of thermal phase transitions, but it's not temperature. It's the reduced temperature-like variable, which is the difference in strain. You could normalize it by the strain, by some strain threshold, but strain's dimensionless anyway. So this is a nice small, dimensionless small parameter. And so that tells us, assigned quantity, how close I am to that line. It vanishes at the line, and it's positive and negative. And presumably, I have some elastic energy which would depend on that and the bending resistance, okay? That's the kind of theory I'd like to have. But for a full disordered system, even in the thermodynamic limit, that might be difficult to come up with. So instead, let's make the following argument. Now, in interest of time, I'm not going to go into the fluctuations and the fact that there's even a diverging correlation length. I'll show you indirect evidence for it, but you see very clear, from the computational systems at least, you see very clear evidence that not only are those fluctuations, and they're not thermal, they're just the non-uniform strain of the system. There was those rearrangements in the cartoon. They both diverge in magnitude and in correlation length, okay? So standard features of critical phenomena. The fluctuations are, of course, not thermal, because everything's still t equals 0. Okay, so the Kadanoff, Kadanoff's idea is just one of these beautiful insights in the history of theoretical physics, right? At least, I'm in awe of it. It's a beautiful, beautiful idea. So he basically says the following. Look, if I have a system near the critical point, rather than characterizing how close I am to the critical point in terms of t, how small that variable is, let's characterize it by how big the correlation length is. There's just some correlation length. And being close to the critical point corresponds to a big correlation length. Being far from the critical point corresponds to a small correlation length. Let's just take correlation length as given. And so if I rescale my system, and by rescaling, it's probably maybe better to think about lowering my magnification. So rather than looking at all the detail, I'll look at it from a distance with lower magnification, and then so a collection of spins on a lattice in a block of size L by L. So L is an integer. It's the number of blocks on a side that I put together, sorry, number of spins on a side I put together in a block. And if I look at that system in low magnification, shown on the right, it should look exactly like the previous system, except the correlation length is smaller, so I'm farther from the critical point. So, in other words, in the interest of time, I'm going to go ahead and use this slide. My new effective temperature variable is now larger than the previous one by some factor. I'm going to assume a power law of this form. Because the other thing you learn is you can compose multiple such rescalings, and I have to get a product-like rule, right? So not necessarily an invertible product, so the term group is a little unfortunate in that mathematical sense, but anyway, it's a product, they compose as products, so basically this is the only form you can have. And likewise, the other thing that controls how close I am to the critical point is how small kappa is, right? That's that field-like variable that takes me away from the critical point. And so that presumably also rescales. And so the theory in the rescaled form should basically look like the previous one at a different temperature and different kappa. I actually want to talk about the energy per unit per cell in the system, though, because once I'm doing the rescaling, I'm going to have a problem accounting for the energies, because the energies are going to be growing just because I'm scaling up, right? So I want to do it per cell. And so trivially, I obviously have to divide by the length, by the scaling factor to the minus number of dimensions to account for the fact that this should look like a single cell now, okay? Put those factors together, and that says that that suggests that the energy, now this is not a free energy, the argument is for free energy originally, but this is just an elastic energy for my athermal system. It should have this homogeneous form mathematically. Okay, now the other thing that happens is the correlation length decreases by that rescaled amount, but if the correlation length, which is observed, if it goes like t to the minus nu, it's not a gamma, that's meant to be a nu, then, so on the one hand, this should go to a scaled smaller correlation length, but it should also be obtained from this. I should get it from t L to this x power to the minus nu. And of course, the t to the minus nu is just that. So the only way this is going to make any sense is if x times nu is 1. So I can immediately identify one of those unknown exponents, x, there, as the correlation length exponent. And continue along these lines. So once I have an elastic energy, though, all I do is take a derivative with respect to strain, and I get a stress. Derivative of a free energy with respect to the temperature-like variable would be an entropy, right? So stress is an entropy-like variable. Two derivatives of the energy with respect to strain. And by the way, it doesn't matter whether I take a derivative with respect to strain or my reduced strain, T. Then two of those would be the stiffness. That's going to look like the heat capacity, two derivatives of a free energy with respect to temperature. And now the point is that that has a simple scaling form in terms of my homogeneous Hamiltonian there. So K should go like L to the minus D plus 2x. X is nu, so this is 2 over nu. So this H20 literally just means take the function h, take two derivatives with respect to its first argument, 0 with respect to its second argument. So it's a new function. Kappa to the L y, okay? And now, so this should hold whatever value of L I use, provided I don't rescale so much that I get out of the critical region entirely. So you should think that this has a limit. In fact, ultimately, that limit is where L is so big that the correlation length has gone to 1. Individual cells are essentially independent of each other, no longer correlated. And so that corresponds to choosing L equal to t to the minus nu. Plug that in here. This combination means this is going to go to either plus or minus 1. Notice this is t without absolute value. This is t with absolute value. And then the kappa here should be, I should divide out by t to the nu y. So that presumably is going to be my phi exponent. So those are the arguments in my function. And so this thing winds up being that scaling function. Okay? So there's my scaling function. But what's really interesting is that if I look at this factor, what is it? So well, let me get rid of that. So that combination right there is t to the d nu minus 2. Just plugging in my choice for this rescaling factor. That should be identified with that. So I've learned that F apparently should be d nu minus 2. By the way, that looks like the heat capacity hyperscaling relation you might remember with the minus sign. So a positive alpha exponent for the heat capacity corresponds to a negative F in our problem. If that sounds slightly odd, remember heat capacities typically diverge, maybe with a discontinuity at the transition. What's the heat capacity for us? It's stiffness. Remember, the stiffness was nice and smooth through the transition. Different sign to the exponent. Has interesting implications in terms of what's called the Harris criterion, by the way. If you're familiar with the importance of disorder. Anyway, but this is all still athermal. Anyway, so this is now new information because independently we can measure the correlation length exponent. It's indirect. I'll show you. It's hard to directly measure, but we can put reasonably tight error bars on nu from the computational work. We can measure F pretty easily, and we can test whether this relationship works. And we can do it in 2D and 3D. 3D took longer for obvious reasons. So on the one hand, this is the stiffness. By the way, accounting for a small discontinuity, I mentioned that. This is the stiffness as a function, well, multiplied by the size of the system. So W, sorry for the mixed notation, W is not the scaling function. It's the size of the system, the width of the box, if you like. To the power F over nu, there's nu. F we can get from the data I showed you before. That's a direct scaling of the stiffness of the system. So by choosing different values of nu that appear on both axes here, you can put estimates on what the value of that is. Basically, the idea, this is so-called finite size scaling. So one implication of this real space picture, it's super useful when you think about computation because it tells you the importance of finite size effects. They're inevitable in computation. It's not a bug. It's a feature. Finite size effects are a feature, not a bug. Finite size effects allow you to identify the correlation length. Very important. So what you do is you study samples over a wide size range. Modest sizes here in 3D, it's tough. In 2D, you can go up to 200 by 200, no problem. 3D is pretty tough. But anyway, so on the one hand, you see, so this identifies a slope of 0.79. Those familiar with this thing may realize that all the data on the extreme left I'm not fitting, that's all finite size limited. That necessarily is analytic because it's no longer critical. So in order to identify the non-analytic features in the behavior, you have to make sure that you're only analyzing data which are not finite size limited. Because any finite system ultimately has an analytic theory. Okay. Anyway, so, and then you get, some distribution of F exponents from that. But here's probably the more interesting thing. this is a nice way to identify the correlation length exponent nu. So what you do is you measure the non-affine fluctuations. You show indeed that they peak at the transition. By the way, notice the orders of magnitude here. And what's more, they're finite size dependent. So smaller systems have a more rounded and suppressed fluctuations, et cetera. Okay. So we basically confirmed that this works with the non-mean field values of the corresponding exponents. And so an interesting implication of that, since it happens in 2D and 3D, is that the upper critical dimension would appear to be higher than 3. And that's very different from jamming. Okay. Now, I know I'm basically out of time, but let me just show you that this has interesting implications for other mechanical things like Poisson ratios. So ordinarily, the Poisson ratio tells you how much typically a system contracts in the transverse dimensions as you extend it in the longitudinal direction to preserve volume. What's been known for many years now for extracellular matrices and actually tissue is that they exhibit anomalous Poisson ratios. Poisson ratio is normally limited on the upper end by 1/2. That's a thermodynamic rigorous bound, but it only applies in linear response. Nevertheless, because a lot of these systems go nonlinear at small strains of order just a couple percent, what people find is a nonlinear sort of Poisson ratio that looks like this. So basically, they contract anomalously large amounts in the lateral direction when you extend them along the axis, meaning that they can expel 90% of the volume, provided you allow enough time for the solvent, whatever it is, or fluid to leak out. And so this is a collagen one. The previous one was fibrin. This is, and the references are here. It's been reported many times over the years. Notice this, well, 80% in this case of the volume is removed. The previous one was about 90. So it looks like a Poisson ratio is anomalously large. Large means contraction. And what we were actually able to show is what Jordan Shivers, who's now postdoc in Chicago, but former group member, showed is that these anomalies in the Poisson ratio, so Poisson ratios people report in the literature of 10, okay? Doesn't make sense from the point of view of linear elasticity. It's not technically linear, so it's not violating any bounds. But reporting this the way it's been reported in the literature, you can account for these very large values of an apparent Poisson ratio, call it nu tilde, of order, well, up to 10 or so. And what's interesting is systematically that coincides with the same phase boundary over there. It's controlled by that same phase boundary. So another critical signature, along with the fluctuations. So what I'm plotting here is simultaneously, let's see, this is connectivity, this is extension along one axis. This happens to be a 2D result. You can do it in 3 as well. It's just, you know, you get better data in 2D. In the inset is the plot of the fluctuations. These two are coinciding. Those non-affine fluctuations are peaking along the transition, coincident with the anomaly in the Poisson ratio. There's other interesting elastic signatures. I'll just end with a comment on temperature effects, which are really cool. So again, the picture I showed you before with the strain-controlled critical point suppressed, or actually you remove the criticality technically, but you know, stabilize the system. If you add bending, you get a critical zone like this. So you could do this, you know, with either the isostatic horizontal axis or with the strain-controlled. And the point is there's many different effects which will stabilize networks. And we've been interested in a number of them. We've just been talking about strain. You could imagine stress as a field which stabilizes the system as well. Fiber bending I told you about before. Motor activity, so internal stress generation by contractile forces also have some interesting implications for coupling to these critical strain fluctuations. But just to hint at an interesting direction is to look at thermal effects. So basically, if you take another effect which will stabilize this floppy phase is to put in thermal fluctuations. And the way to see that is the classic picture of entropic elasticity. Take a freely jointed chain, no energetic penalty for different shapes, no resistance to stretch as a chain, turn on temperature, and you get resistance. And it's always proportional to temperature, right? Because a free energy has an energy minus TS term. If there's no energy, this was an entirely floppy system to begin with, then everything is proportional to T. In fact, anything you derive from entropy, including all the mechanics. What happens if you turn on these temperature in these systems? And there's actually been rather little work along those lines, but let me just show you. One of the first things we could find was in the 90s, Pliszka and his group looked a little bit at basically the Maxwell picture at finite temperature. Anyway, here's what happens. Actually, I'll just show the sort of phase diagram. And we now see this with the strain control transition as well. This happens to be the isostatic one, a little bit easier initially to study. So at high connectivity, you get a stable system. There's no dependence on the temperature. It's all mechanical. Low temperature, I would get a floppy phase, entropic elasticity. But the weird thing is, the modulus is not proportional to T. It's proportional to T to the 0.8. And then there's a critical region. But the way we understand that 0.8 is the following, and I really will end with this. I know I'm going over. The argument about the freely jointed chain is as soon as I turn on temperature, it can fluctuate, and then entropy starts to become relevant. The way you can understand this anomalously low dependence on T is if the entropy varies as T to the minus 0.2, a very weak decrease. Because free energy has this additional T factor. And what's happening here is the following. In a freely jointed chain, I don't have any of this, and that's because every joint, in terms of the conformations, every joint is free to rotate independent of what the rest of the conformation is doing. I'm not constraining it at the boundaries. It's not true as soon as I have a higher dimensional object. If I've got a meshwork, a fishnet, or a 3D equivalent thereof, any thermal fluctuations that are generated start constraining the remaining fluctuations. And so there's a weak suppression of the number of states available as the temperature goes up. And that accounts for this. And we now have evidence that this is happening in well, seems to be 2D, 3D, and it also happens qualitatively, again, with a sublinear anomalous entropic elasticity for what was a floppy regime here.
Is it also an effect that depends on the size of the fluctuation? But why does it go away?
Why does it go away? Oh, well, so this is basically saying, so it's getting large. It's a large effect. I'm suppressing the entropy at high temperature.
It grows essentially like T, right?
It's slightly less than linear, the modulus. So that modulus is still coming from you can show that the energy term is not dominant, by the way, in that regime. So it's all still entropy. So it's still entropic elasticity. It just happens not to be proportional to T.
I mean, between 0.8 to 1, when you reduce the power.
Oh, going up there. Yeah. So ultimately, when the temperature gets high, it does go to a linear regime. By the way, I got to say, one way in which this is pretty hard to identify is the following. As soon as you add thermal fluctuations to a network with nodes, you start getting a trivial ideal gas pressure. You need to look at off-diagonal terms in the stress in order to see this effect. Okay? It can be utterly dominated by the trivial ideal gas pressure, which is proportional to T. That winds up being a little hard. So we focus on mechanical quantities which are derivatives with strain of some kind. Okay. got to thank a whole bunch of, you know, been so happy to have so many great former group members over the years working on these various things. Been fun.
Okay, so let's thanks.
As well as multiple experimental collaborations, which we get a lot of inspiration from.
So Fred, thanks for being with us. It was great.
I enjoyed it.
Great 4 lectures. And now I would like to know if you have any other questions.